Chemistry, the science of matter, thrives on understanding how atoms interact to form molecules. This interaction is the cornerstone of countless phenomena, from the simplest reactions in a test tube to the complex processes that sustain life. This intricate dance of electrons governed by the laws of attraction and repulsion is what we call chemical bonding. Electrons with their negative charge are drawn to the positively charged nuclei of atoms, creating a delicate balance that holds molecules together. It's the foundation upon which the grand edifice of chemical reactions and molecular diversity is built. Without chemical bonding, the rich tapestry of compounds and materials we see around us would not exist. For JEE aspirants, mastering the nuances of chemical bonding is not just an academic pursuit, but a strategic imperative. Understanding these concepts can be the key to unlocking higher scores and achieving your academic goals. In our previous exploration, we delved into the fundamental concepts of ionic and covalent bonding, unraveling the forces that bind atoms together. We examined how these bonds form and the energy changes associated with them. We learned how the transfer of electrons leads to the formation of ionic compounds, while the sharing of electrons gives rise to covalent molecules. These basic types of bonds are the building blocks of more complex interactions. Now, we embark on a journey deeper into the realm of chemical bonding, equipping ourselves with the knowledge and tools necessary to tackle the challenges of the JEE examination. This journey will take us through advanced concepts and their applications. This comprehensive guide will serve as your compass, navigating you through the intricacies of molecular orbital theory, hybridization, VSEPR theory, and more. Each of these topics adds a layer of understanding to the complex world of chemistry. We'll unravel the mysteries of resonance, dipole moments, and bond parameters, providing you with a solid foundation to understand the behavior of molecules. These concepts explain why molecules have specific shapes, reactivities, and properties. So, fasten your seatbelts and get ready to dive into the fascinating world of chemical bonding, where we'll unravel the secrets that govern the interactions of atoms and molecules. This journey promises to be both enlightening and rewarding, paving the way for your success in chemistry. While the Lewis dot structures and valence bond theory provide a basic understanding of bonding, they are just the tip of the iceberg when it comes to the intricate world of chemical interactions. Molecular orbital theory, or MOT, offers a more sophisticated and accurate picture, delving deeper into the quantum mechanical nature of molecules. This theory postulates that atomic orbitals combine to form molecular orbitals, which are spread over the entire molecule, providing a more holistic view of electron distribution. These molecular orbitals are of two types, bonding and antibonding. Bonding orbitals enhance the stability of the molecule, while antibonding orbitals can have the opposite effect. Bonding molecular orbitals are lower in energy than the atomic orbitals from which they are formed, contributing significantly to the stability of the molecule by allowing electrons to occupy a more stable state. Antibonding molecular orbitals, on the other hand, are higher in energy and destabilize the molecule. This destabilization occurs because electrons in these orbitals are less tightly bound to the nuclei. The filling of electrons in these molecular orbitals follows specific rules such as the Aufbau principle and Hund's rule. These principles dictate the order in which orbitals are filled, ensuring the most stable configuration. MOT successfully explains certain phenomena that valence bond theory fails to address, such as the paramagnetic nature of oxygen. This is due to the presence of unpaired electrons in the molecular orbitals. It provides a more comprehensive understanding of bond order, bond length, and bond energy, which are crucial parameters in determining the strength and stability of a molecule. These parameters help chemists predict how molecules will behave in different environments. In essence, MOT provides a powerful framework for understanding the electronic structure of molecules, enabling us to predict their properties and reactivity with greater accuracy. This predictive power is invaluable in fields ranging from materials science to pharmacology. It's a concept that goes beyond the limitations of simpler models, offering a deeper insight into the nature of chemical bonding. By embracing the complexity of MOT, scientists can unlock new possibilities in the design and synthesis of novel compounds. Imagine an artist blending different colors to create a new hue. Similarly, atoms combine their atomic orbitals to form hybrid orbitals, a process we call hybridization. This mixing of orbitals allows for stronger bonding and more stable molecular geometries. The most common types of hybridization encountered in organic chemistry are sp, sp2, and sp3. In sp hybridization, one s orbital and one p orbital combine to form two sp hybrid orbitals, oriented 180 degrees apart. This results in a linear geometry as seen in molecules like acetylene. sp2 hybridization involves the mixing of one s orbital and two p orbitals, generating three sp2 hybrid orbitals that lie in a plane, 120 degrees apart. This arrangement leads to a trigonal planar geometry, exemplified by ethylene. Lastly, sp3 hybridization combines one s orbital and three p orbitals, forming four sp3 hybrid orbitals directed towards the corners of a tetrahedron. This tetrahedral geometry is characteristic of methane. Understanding hybridization is key to predicting molecular shapes, bond angles, and ultimately the properties of compounds. Section 4, V.S.Epper theory, predicting molecular geometries. The three-dimensional arrangement of atoms in a molecule, known as its molecular geometry, plays a crucial role in determining its physical and chemical properties. This arrangement influences how molecules interact with each other, their reactivity, and even their color and phase of matter. The valence shell electron pair repulsion, or VSEPR theory, provides a simple yet powerful tool to predict these geometries. By understanding the repulsive forces between electron pairs, we can determine the most stable arrangement of atoms in a molecule. The central idea of VSEPR theory is that electron pairs in the valence shell of an atom repel each other and will arrange themselves to minimize this repulsion, thereby determining the shape of the molecule. This principle helps us predict the angles between bonds and the overall shape of the molecule. For example, in a molecule with two bonding pairs of electrons and no lone pairs around the central atom, like carbon dioxide, the electron pairs will be farthest apart when they are on opposite sides of the central atom, resulting in a linear geometry. This linear arrangement is crucial for understanding the molecule's behavior and interactions. Similarly, in a molecule with three bonding pairs and no lone pairs, like boron trifluoride, the electron pairs will be farthest apart in a trigonal planar arrangement. This geometry is essential for predicting the molecule's reactivity and how it bonds with other molecules. The presence of lone pairs, however, introduces distortions in the geometry. Lone pairs occupy more space than bonding pairs, leading to adjustments in bond angles and overall shape. For instance, water has two bonding pairs and two lone pairs around the oxygen atom. The lone pairs, being more diffuse than bonding pairs, exert greater repulsion, pushing the bonding pairs closer together and resulting in a bent molecular geometry. This bent shape is responsible for many of water's unique properties, such as its high boiling point and surface tension. The lone pairs, being more diffuse than bonding pairs, exert greater repulsion, pushing the bonding pairs closer together and resulting in a bent molecular geometry. This bent shape is responsible for many of water's unique properties, such as its high boiling point and surface tension. Understanding VSEPR theory is crucial for predicting the shapes of molecules and rationalizing their properties. By mastering this theory, students can gain deeper insights into the behavior of molecules, which is fundamental for fields ranging from biochemistry to materials science. This knowledge is not only academic but also practical, aiding in the design of new drugs, materials, and chemical processes. Section 5, Resonance, enhancing stability through electron delocalization. Imagine a group of musicians playing different notes that blend harmoniously to create a richer sound. Similarly, some molecules exhibit a phenomenon called resonance, where electrons are not localized between two atoms but are delocalized over multiple atoms or bonds. This delocalization contributes to the stability of the molecule. Resonance is represented by drawing multiple Lewis structures called resonance structures, which differ only in the arrangement of electrons, not in the position of atoms. The actual molecule is considered to be a hybrid of all the contributing resonance structures. For instance, benzene, a cyclic molecule with alternating single and double bonds, is best represented by two resonance structures. The electrons in the pi bonds are delocalized over all 6 carbon atoms, resulting in equal bond lengths and a highly stable structure. Similarly, the carbonate ion exhibits resonance, with the double bond delocalized over all 3 carbon-oxygen bonds, contributing to its stability. Section 6. Dipole moment, understanding molecular polarity. In a tug-of-war, the direction of the rope's movement depends on the relative strength of the two pulling teams. Similarly, in a molecule, the distribution of electron density determines its polarity. Dipole moment, a vector quantity, measures this polarity. It arises from the unequal sharing of electrons between atoms in a covalent bond. The atom with higher electronegativity attracts the shared electrons more strongly, creating a partial negative charge on itself and a partial positive charge on the other atom. This separation of charge creates a dipole moment, represented by an arrow pointing from the positive to the negative end. For example, in hydrogen chloride, chlorine is more electronegative than hydrogen, so the dipole moment points towards chlorine. Molecules with a net dipole moment are polar, while those with zero dipole moment are nonpolar. Dipole moment plays a crucial role in determining the physical properties of molecules, such as boiling point, melting point, and solubility. Understanding this concept is essential for predicting the behavior of molecules in various chemical and biological systems.